Hello there, children. I am at home sick today. However, I am going to show you how to construct your error analysis table. Why? Because you know I love you and I'm a dedicated educator. So, hopefully you can see that I'm on Moodle, right? So I'm going to go to, also I haven't used this program before, which is kind of cool. I think I can do fancy things like, get a general lab resources, and then go to the guide for lab writing. So, oh god, how do I get out of that thing? So I clicked on the guide for lab writing, and now this is where I showed you that you can see the table of contents over along this side. And so what I want you to do is I want you to go to where it says error analysis. And so I am going to go there now, error analysis. And if you look, this is how it talks about how to write your error analysis section. And so to calculate your percent error, which you do need to do for this lab, you need to look at this. This should be very, very familiar to you by this point. It's going to be experimental minus actual divided by actual. And you have all of the actual numbers in the lab for you. So depending on which metal you think your specific heat lab is, you can figure that out. So, oh, hello. All right, what else we've got? So, like I told you in class, your error analysis section is not going to be in paragraph form. I'm not going to read it if it's in paragraph form. It's too hard for me to find all the information. So what you're going to do is you're going to construct a data table, and it's going to have, let's see if I can do more fun stuff. Let's see. How about a red arrow? All right. So you're going to construct your data table, and it's going to have your source of error. And like I told you guys, you need to have 3 sources of error, valid sources of error for your lab. So boom. You need to explain how your source of error affected your data. So if you can't do that, and I have had students write it up where they're like, I don't know. Well, that's nice. That means it's not an error source. It also says effect on results explained. So that's like an explanation part. And then connection to percent error or percent yield. You are not doing percent yield for this one, so this is going to be your connection to your percent error. And you need to give a quantitative change to your percent error. What that means is, did it make it go up or down? And it's perfectly acceptable that you say it got closer to the actual number. Hey, that's an error that worked in your favor. Not a big deal. And then, of course, you need to have some sort of realistic improvement. So, this is an example on the synthesis of acetylsalicylic acid, which is aspirin. And if you guys take organic chemistry, you're actually going to have that. There we go. All right, so what you've got is you've got your error analysis table, right? So an error source. When you're making acetylsalicylic acid, what you need to do is you end up with all of this aspirin, and it's in solution, and you need to dry it to make sure there's no water left in it. So one source of error would be, for example, the substance was only dried for 1 hour. You probably want to dry it for longer than that, and what that meant was there was still some liquid in with your aspirin. So that's a valid source of error. And then if I look over here, it meant that the substance was wet when you measured it. So what that meant on your data is that it changed your mass higher, okay? So again, this is all about your data, okay? So right here, we're talking about data. If we look over at this one, effect on results explained, it says high mass, right, made it seem like you got more product than you were supposed to. So this is a percent yield lab. Yours, you're going to link it to your direct calculation of the specific heat. So for example, let's see if I can do this. Yes, buddy. M delta T C P. So if your mass was too high, right, what that would mean was that this whole value, because they're all multiplied together, oh god, because you're calculating for specific heat. Hang on. Oh, hello. Okay. Let me get rid of that. Shh, don't tell anyone. Okay. This would make more sense. Q over M delta T. So, if your mass ended up being too high, this is just an example. You should not use this as example. It's a really bad example. If your mass was too high, what that would mean is your denominator number got higher. So CP, your specific heat, would end up being lower than it should have been. Now this could be a good thing, right? Because if your specific heat, let's say the actual, forgive me, I don't have a stylus. Your actual was, I don't know, this is terrible, 3 joules per gram degree C. But your value, ended up being 3.46. I'm just making stuff up here, joules per gram degree C. Because your specific heat ended up getting lower, it actually brought you closer to the true value. And that's a good thing. So, well, I mean, it's a source of error, but it brought you in the right direction. So, you see what I'm saying? So anyways, so that's just a better example on yours, how you could link it. So again, right here, effect on results explained, you're going to have to somehow link it to this expression. Cp equals Q over M delta T. Now, connection to your percent error. What that meant is, in the example that I just wrote out, because your number was brought down by your error, it actually made it a better percent error for you. Because you can imagine if you did get this M right, say your number was like 3.5, now you're getting further away from 3, so that's not a good thing. So this whole, you're going to say mass got higher, my percent error got lower because your specific heat, right, got closer to the true value. Realistic improvement, I don't know. This is a really bad example, like I said, but don't use things like, where's my eraser friend again? There it is. Don't use things, how do I erase? Oh, dear mother of God. Okay, hang on, time out. I can't erase anymore. All right, cool. So don't use things like, I didn't tear the balance. Here, I'll write it, actually. Hang on. Go back. Like I said, I have not, oh, hello. I haven't used this before. Don't judge me. All right. Here, I'll write in green. I didn't tear, which means zero out, right? The balance. Don't use stuff like that. Why? Because I'm going to be very curious why you didn't tear the balance. That's kind of something that everybody should do and know how to do. Don't say things like, I didn't read at the meniscus. Yeah, that's also something you should know how to do by this point. Things that you should think about in terms of your source of error include, for this one, think about what your system is. Oh God, that was bad. And what your surroundings are. Oh, that's even worse. Because when we talked in class, we talked about how the system is going to be the actual reaction. So that's going to be where your hot metal is giving off energy to your water. But think about what the surroundings are. Think about what some things could be that may or may not have absorbed even some small amount of heat, because that could be a source of error for you. That would change your Q, right? And then you can talk about how Q is changed. Then you could also talk about, like here, energy was absorbed by the air. That means that the amount of heat transferred from the metal to the water was lower than it should have been. Ditto here. So this meant that Q was lower than it should have been. Connection to percent error. If Q is lower than it should have been, right, and it's a denominator, that would make your specific heat lower. And then you can talk about how it related to your true value. And then realistic improvement, try to be a bit quicker in the transfer from the metal, of the hot metal to the room temperature water, something like that. So I hope this helps you with your error analysis table. I'm really sorry I couldn't be there today. I will be in tomorrow, I promise. As you can probably tell, I'm just not feeling very well today. So yeah, if you have any questions, save them for tomorrow, but I was hoping that this might at least get you going in a good direction so that you can finish your lab for Friday. All right, signing off. Let's see, can I do something fun before I sign off? What's this thing? No. What's this thing? No, these are all stupid. Hang on. I want to see something cool. No. Yeah, everything's kind of lame. My bad. Sorry, we lose. What's this? I want to do that. Whoa. Because star. Okay. All right. Signing off. I will see you guys tomorrow. See you later.